Good day, everyone. My name is David Williams, Executive Director of the United States Association for Energy Economics. It gives me great pleasure to welcome you to today's webinar entitled, Can Macroeconomic Models Really Model a Low-Carbon Energy Transition? We are grateful to our moderator, Dr. Carey King from the University of Texas at Austin, and our distinguished panelists for today's timely discussion. We are also grateful to the University of Texas at Austin for sponsoring today's webinar. First, a little bit about the United States Association for Energy Economics. We are the largest affiliate of the International Association for Energy Economics and provide a forum for the exchange of ideas, experience, and issues among professionals interested in the field. The organization produces 2 professional journals, a newsletter, and holds conferences and virtual presentations on a wide variety of energy economics issues. If you're not familiar with the organization, we encourage you to visit www.usae.org and learn about our products and services. A few housekeeping matters in regard to today's webinar before I hand things over to our moderator. First, this webinar is being recorded for those that cannot participate in today's live event. If you have questions for our panelists, please click the Q&A button at the bottom of your Zoom window and type your question. We've allocated sufficient time at the end of this webinar to address your questions. And now I would like to introduce you to our moderator, Dr. Carey King, research scientist and assistant director of the Energy Institute at the University of Texas at Austin. Carey, over to you.
Okay, thank you, Dave. Thank you very much for having this. I'm going to give a quick introduction to our speakers and make some opening remarks, and then they will also make some opening remarks as we discuss essentially the capabilities of macroeconomic models and their incorporation of energy, and specifically we could ask, do they have the capability of modeling something like a low carbon energy transition? So today it is a privilege to have these 2 individuals. We have Steve Keen, who's a professor of distinguished research fellow at the Institute for Strategy, Resilience, and Security at the University of College of London. He's author of Debunking Economics and Can We Avoid Another Financial Crisis? He's put a lot of effort into thinking about the role of private debt and its influence on the economy. And because of that, he was the winner of the Revere Award from the Real World Economics Review for being the economist, as it says here, quote, who first and most clearly anticipated and gave public warning of the global financial collapse, and whose work is most likely to prevent another global financial collapse in the future. So we can try to apply that line of thinking as well to thinking about the energy systems. We also have David Daniels. David Daniels is visiting researcher at Chalmers University of Technology, and he's from the role he had when I met him, he's the former chief energy modeler of the Energy Information Administration. So he has a long background and a deep knowledge of the ways in which people think about modeling the interaction of energy systems and the economy. So with that said, I'll make some opening remarks and then pass it over to Steve and David for some opening remarks before we go through some other questions. So the interest from my perspective, and I guess I can roughly plug my latest book, The Economic Superorganism, published by Springer, which is on the topics similar to many that we'll have today. The thought is, how do we think about the interaction of the energy system with the broader economy? And from a simple standpoint, I think of it as follows. Energy largely runs and defines what the economy is, in the sense that machines require energy to operate, and the economy is largely about moving things and reshaping things and moving things around the economy. Then our definitions of what the economy is inform policy. The policies we make, therefore, in turn, define impacts and affect impacts within society and people's livelihoods. And then these impacts on society and people's livelihoods might and desires might therefore in turn feedback and affect how we use energy, such as pushing for low carbon energy, for example. And what this comes down to a large degree is thinking about economic growth models of the economy, which say, if you do these things, how do we think the economy is going to grow? These therefore impact our policies and affect the affect our perceptions of how effective policies are at achieving one goal or another, and energy-related goals are just one of those. But if they don't treat energy properly within the models, then we could ask, are they giving us a true representation of how the role of energy plays, the role of energy as it plays in the economy? So I'm a little worried that models we're using to assess the economy and say for modeling a low carbon transition are not up to the task for the questions that we're asking of them. Part of this, we might need to think more about how the economy has physical properties and requirements in the same way as biological organisms, or we might be able to learn from other areas of study to inform how we're thinking about how the economy operates. And I'm just showing one slide as my introduction here. On the left is a representation of the basal metabolism of animals on the y-axis and the animal's mass. And they go through these growth stages. As an embryo, like a fish embryo, you might increase your mass, say 10 times, and the energy consumption, metabolism of that embryo might go up also 10 times. So there's a proportionality there, m to the first power. As animals grow and create structures within themselves, like organs and distribution systems, like the circulatory system, this turns into what we call a sublinear growth regime, where as the mass increases, the energy consumption or the metabolism grows more slowly than the mass. And this same type of trend is observed in the economic data, in the sense of when we had a smaller economy in the beginning part of the 20th century, we had more of a linear growth regime where GDP would increase, say 10 times, and primary energy consumption would also increase 10 times, or a approximate linear relationship. But then since the 1970s, we've had a sublinear relationship that's more representative of adult animals. So this is an example of some things we can learn or perhaps apply and understand how to apply these principles from other physical systems that have to take in energy to structure themselves, maintain themselves, and grow, just like the economy does. So we can ask, is the economy governed by the same principles as organisms? So I will stop there and then go to Steve for his introductory remarks, and I'm sure we'll touch on many other topics during this webinar. Steve, over to you. Steve, do you hear me? Steve is in Thailand, so there may be some delay. Unmute yourself. Steve, you're on mute.
Rebecca, could you unmute Steve, please?
I've already sent a request for him to unmute through the.
All right, we'll go to David for now. Oh, there's Steve, I think now.
It's unstable. Is it okay?
It's a little off, Steve.
Okay, if you could.
So, well, let's go to David for now, and then come to Steve after David.
Thanks, Carey. Thank you. First of all, thank you for setting up this webinar. I think this is a very timely topic, a very important topic. I come at it not from the standpoint of a macroeconomic modeler, but as you said in my introduction, at the Energy Information Administration, I'm coming at this from the standpoint of an energy modeler, looking at macroeconomic models and insofar as they interact with energy models to tell us something about the future. The important thing here is that none of these models that we're talking about, macroeconomic models, energy models, none of them tell us the future. What they do is they represent historical relationships. Virtually every model, a macro model, energy model, regardless of its type, is calibrated, specified with historical data. I've seen a lot of macro models that use data going back to the 1970s to get enough data to establish the relationships between the macroeconomic variables. And therefore, when they're projected forward into the future, they're telling us not so much about what's going to happen in the future, but what has happened or how these relationships have behaved in the past. I think that's really dangerous when we're talking about a transition. The transition is by nature not an incremental change, but a structural break. And what we're talking about with the energy transition is a structural break in the energy system. And as that break feeds back through the macroeconomy, the relationships from the energy to the macroeconomy, and also from the macroeconomy back into the energy system, may be very different from what they've been historically. That's the problem we face in trying to model this. I think the strict answer to your question, can macroeconomic models really model a low energy carbon energy transition, a low carbon energy transition? I think the strict answer is no, but a more nuanced answer is they can tell us something. And what is it that we can learn from these models that is helpful in when we're developing policies and thinking about managing that transition? You're muted, Carey.
Thank you, David. Steve, we'll give it another go there for your intro.
Okay. Let's see if we're lucky with the slide, with my sound this time.
Sounds good for me.
So-
Go ahead.
Okay, so you put up my first slide there if you can, Carey.
Yeah.
Okay, this is just showing just how tightly correlated change in energy and change in GDP are at the global level. That correlation coefficient there is 0.83. You can see causation going both ways, of course. There's a plunge, as you can see, at the time of the financial crisis. That's where, let's say, the economy caused less energy consumption. But you can go to the 1980s and 1973 and say that the massive change in oil prices caused by OPEC was the factor that caused the decline in GDP. So it works both ways. But it's incredibly tightly coupled. And if you were working from first principles and empirical data, you'd be looking for a very strong link between energy and GDP. Next slide, Carey. And when you look at it, amazingly enough, over a quite substantial scale, from back from 5,000 roughly million tons of oil equivalent through to 15 roughly million tons of oil equivalent, it's almost a straight line relationship between energy consumption and GDP. So that would tell you your economic model, the mathematical relationship you have between energy and GDP could be virtually 1-for-1. Next slide. Okay, the type of model we actually have in most economic models is actually the very top one up there, the red one, very strongly curved. That's a Cobb-Douglas reduction function. And most of these models presume you can produce by combining labor and capital with no energy. When they have done, by that I mean neoclassical economists who use this particular rendition of production, when they have included energy as a third factor, the weight they give to it is based on the share of energy in GDP. And that's the same way they work out the labor coefficient and the capital coefficient. Now, that share being about between say 5 and 7%, but say 5% as a rough idea. That tells you that if you had an 80% fall in your energy input, you'd only suffer a 10% fall in GDP, which of course is arrant nonsense. But that's the sort of mathematical model that sits behind almost all, I presume virtually all, if not all, the neoclassical models that attempt to model the energy transition. The blue line is what happens if you take my insight into account from the paper in 2019 called The Note on the Role of Energy in Production, which says that, in a little cat line, energy, labor without energy is a corpse, capital without energy is a sculpture. So you have to say that the labor and capital are means by which energy is converted into useful work. Now, when you do that, you get a coefficient for energy of capital share, which is about 30%. So that gives you the blue line, and that tells you an 80% fall in energy would cause a 40% fall output, which is more realistic, but still well short of the empirical data. The final one, I'll leave the third one out. It's a bit of I can talk about that if anyone wants to ask me about it, but the main one is the straight line. That is the Leontief relationship, a 1-for-1 relationship between energy and production. Once you take into account that machines are a means of converting energy into useful work, you get a 1-for-1 relationship between the two. Now, that's what we should be using to model the impact of an energy transition. And only the post-Keynesian models, of which there are a handful and nowhere near as developed as the neoclassical, only a handful of those use that right model. So what you have is the top line is the curved line is fundamentally what economists are using to say what will be the impact of a large fall in energy, and it's trivial. So yet again, economic theory trivializes a major danger coming our way, because I think reality lies in the gap between the curved red line and the pink line, and that's, we might be expecting, courtesy of economic models, a very small impact from a fall in energy if we have to go from fossil-based fuel to what we have as currently renewable. We're going to face a far larger shock. And I'll leave it at that.
Okay, thank you. So we'll open up, you kind of blend into maybe a nice starting question. You brought up the idea of useful work, and for some of us in the studying this area, we know what that means. Some people call it useful exergy if they want to get really nerdy a little bit. But useful work is essentially, say, the final end-use fuel energy that goes into a machine like an internal combustion engine or an electric motor in the power plant, that then ends up as a sort of mechanical work on the outside, the spinning shaft of a drive. Could be electricity coming out of a power plant, the high temperature heat that goes into a chemical facility. So the useful work is this final form of often mechanical energy that drives some process. And by thinking about fuel and the efficiency, you've incorporated this technological parameter, say conversion efficiency, which has thermodynamic properties, or at least we can understand it from the concept of thermodynamics and engineering and science. And so that makes this linkage between useful work and GDP. And as you stated, Steve, some work done in this area, and a lot of it by Robert Ayers and some groups, and then an Exergy economics group in Europe is looking at this, and several countries study basically show if you estimate useful work and then plot it against GDP, you get close to this one-to-one relationship. So you have this physical explanation seeming for explaining GDP, which you say is closer to your pink line. So, question to both of you, Steve, I guess you were implying this, but, should we be trying to make macroeconomic models have this more explicit relationship, or at least explore this explicit relationship in historical data? And David, was anybody at the EIA talking about this, or any other people coming to you thinking about this? Are they talking about these ideas? David.
Question for David, was it?
Both of you. We'll go with David first.
Fine.
Okay.
I've read the literature, talked to people that were looking at exergy, but I'm going to tell you that from my personal perspective, and certainly when I was in my time at EIA, I don't speak for them now, but when I was there wasn't any real thought of incorporating the concepts of exergy or useful work out versus work into the model, simply because they weren't seen as being particularly predictive of the future. While they were interesting correlations, historically, it was difficult to understand how those concepts related to the decisions that people were making. And specifically what that whole line of reasoning fails to incorporate are things like prices. And fundamentally, what EIA was trying to do was project the energy system as it was governed economically through prices. And it was difficult to see how you could incorporate both the concepts of exergy and the concept of prices. Those seems to be almost diametrically opposed. And when we looked at the decisions that people were making, they were making them primarily for economic reasons, not on fundamental conservation of energy kinds of reasons. So I think that was how we were looking at it. Having said that, it's an interesting way of looking at historical evolution, and it might be something to be learned in other developing economies outside the U.S. And that is an area that the EA is really interested in, because the U.S. economy is fairly mature, but there's a lot of economies in Asia, in Africa, that are transiting the same path that some of the more developed economies have already tread, but they're doing it from a different starting point in time, a different starting point in technology. And so a big question is for the EIA and other places as well, how will they develop? Will they develop along the same path, or will they be develop along a different path? And if the concept of exergy is one that can help answer that question, I'd consider it.
Let me have one follow up and then go to Steve's comments. So David, would you be saying, well, if I'm going to try to, I don't know, projecting some future scenario in an economic model, projecting the efficiency of devices is in some sense equally as unknown as projecting resources or any other kind of metric technology change?
Well, they're both important. They're both important, but understanding that the behaviors that people, the end uses that people are using energy for is extremely important. For instance, if you look at a developing economy in Africa, they've got industrial sector demands, they've got residential commercial sector demands. As they develop, as the economy develop and incomes rise and people get richer, can start having more disposable income, they buy air conditioners. Well, that's going to drive up the demand for electricity, surely. But did their income rise first? And if so, how? How did their incomes rise? Did it rise because there was growth in the industrial sector, which provided people jobs and incomes and gave them the ability to buy air conditioners and consume more? So did the consumption start in the industrial sector and flow, industrial and commercial sectors, and flow into the residential? Or does sort of a rising tide raise all boats, and rising incomes inevitably drive demand, and that creates the demand for more industrial goods? Does it go that direction? And it's a little bit unclear which precedes which influence precedes which.
Yeah, I think I'm a little bit for the co-evolutionary type perspective as well. But Steve, any other comments on this topic?
Well, I think that reflects the biases of economists to believe everything can be solved by the price system. And I think that's if you see the emphasis economists put upon carbon pricing, it's presuming the price system is the rationing system for quantity in our economy, and getting the price signal right is the main thing that matters. I'm quite a skeptic of that attitude, coming from a non-orthodox economics point of view. And I think because we've left the transition away from fossil fuels so late, and we know how much carbon, roughly speaking, we can allow into the atmosphere before we hit 2 and even more degrees above pre-industrial levels, I don't think the price system is anywhere near fast enough to cause the changes that are necessary. And I think models that don't include energy aren't going to give you that warning. But if we have energy included, and you see our dependence upon continued use of fossil fuels to generate the output we use, given an incredibly strong link between energy and GDP, I think we're going to be forced to say, well, the quantity that matters most is the quantity of carbon. Let's set quotas on that basis. Let's not try pricing. Let's try quotas. And I'm supporting development of what's called total carbon rationing, where we basically allocate a universal carbon credit, which is used as a parallel currency. You have to use both money and carbon credits to buy anything. And if you run out, then you have to buy off somebody else in a trading system, which would put the load on the transition on the wealthy, because of course the poor would not consume anywhere near the average budget for their country, and right up to 95% of the population, you would be below the average, given the skewed nature of income distribution. So I think we have to include energy in our models, and we have to include distribution of income as well, to have any idea of the impact of trying to go through this transition at the speed that is going to be necessary.
Yeah, I think I think there's both good points that both of you made. When I think of the energy, in some sense, not really the first energy transition. Maybe I can think about it as the second one, which is a transition to fossil fuels from agrarian, being the first energy transition, perhaps being able to have an agrarian society and provide food through farming. The cost of energy, if you say energy spending divided by GDP, and for the longest data series we have for England and UK was 50 or 60% of GDP, well, at least as a metric relative to GDP, was how much was spent on providing useful work or providing work services or energy services. And then it's declined to less than 10% for the use of machines and fossil fuels. So really that was, machines and modern fuels replacing animal work and human work with muscle work. And now we're talking about replacing mechanical machines work with a different form of primary energy. So at least that's the way I try to think about it. If I can understand the historical one, and with the incorporation of concepts like efficiency and exergy, maybe I got a better chance of projecting the future one. I don't know if anybody has any comments on that. Otherwise, we'll move to another question.
As long as we're on the topic of primary energy and final energy, there was a comment in here from Pierpaolo Cazzola, actually, which was a good one in the Q&A, and he pointed out the problems with dealing with using primary energy as a metric for or as a relationship between primary energy and economic growth. It's a fair point. I personally prefer final energy for that very reason. His point is that when you're looking at primary energy of some of the new energy sources, the non-fossil fuel energy sources, there's a little bit of arbitrariness, which has been discussed in the literature about how exactly you get the primary energy of nuclear or solar or wind. What does that actually mean, sort of ontologically? And I think for that reason, I think looking at final energy is probably a little bit more robust if you look at it historically and then try to project it into the future. But it's harder to find time series data on that as well. So take it with a grain of salt when using primary energy. Understand that in a lot of projections going forward, you see primary energy falling for two different reasons. One, because final energy is actually falling as a function of GDP, because of energy conservation, because of technology improvements and efficiency improvements. That's one reason. The second reason is because of switching from fossil fuels, which have due to the inefficiency of thermal conversion, have an apparent higher primary energy than some of the renewable fuels, depending on the conversion equivalence of the renewable fuels into primary energy. It's a bit of a wonky topic. It's probably not worth going into.
A bit, but yeah, it's an important one for people in the business, as you say. And I think that's one of the advantages and one of the drivers for looking at something like useful work or useful energy is it's a much more consistent definition than primary energy. So if you're going to put an energy concept into an economic model, it's a more consistent definition. All right. So if we're thinking about, we're going to somehow quantify energy, final energy, useful work, primary energy, whatever it is, and we have some equation or some model that says this is how big the economy is. A lot of times there are, in these models, aggregate production functions, something that Steve was talking about in his introduction. There's some equation that says there's some capital and some labor and maybe some energy or useful work, and we multiply these together in some way to project or estimate GDP. So this is an open question. Maybe we'll start with Steve. What are, I guess, the pros and cons of using an aggregate production function? You could perhaps go into defining what that is, but we're lumping all capital into one number and lumping all labor into one number and all energy into one number. What are some of the pitfalls for that? And should we get away from it, or should we use it with caution? Unmute, Steve.
I've had that question on my mind for a long time, and I think I answered it fundamentally by doing that empirical work and seeing how close that correlation is between energy and GDP right now. If there was a large gap, if there were obvious periods of inconsistency or different trends, then I'd say yes, the aggregate production function, guilty as charged, Your Honour. But given that very, very tight correlation at the international level, then I think you can say, well, even though GDP is a very highly criticised measure, the energy is actually quite accurately modelled, accurately estimated, and they fit together very tightly. So I think an aggregate production function has some merit, but it's got to be one that fits the data. And that's the trouble. The Cobb-Douglas production function monumentally is wrong compared to the data. So it's stuck with, for what I'd call ideological reasons in neoclassical economics, not because it actually fits the information. So we're using an aggregate production function, which I can in general defend, but the particular form that dominates, no, I can't.
I got to say, as an energy modeler, I'm bemused when macroeconomic modelers use a single energy product. E, it's always called E for energy. As an energy modeler, look, oil and gas are just not substitutes for each other. right? Not on the demand side. On the supply side, absolutely, they're co-produced. On the demand side, they're just not substitutes. There was a really interesting study. I think it was the Energy Modeling Forum, if you're familiar with that. Stanford's Energy Modeling Forum did a study. It was EMF number 32, a couple of years back, about 2016. They published the results in about 2018. And it was a study that looked across a panel of macroeconomic models, macroeconomic and energy models. Most of the models were CGE types models. Some of them had more or less robust, detailed representation of energy. The EIA model, the National EIA model, NEMS, was also one of the studies, one of the models in the study. It was different in that it was fundamentally an energy model with a macroeconomic. It was actually kind of an econometric approach. So a very different structure macroeconomic model attached to it. But some of the CGE models were coupled with energy models. So they kind of ran back and forth. So there's a spectrum of detail in the energy sector across these models. There were about a dozen models or so. And what was interesting about them was that they, although they we're looking at impacts on the economy, distributional impacts, impacts of revenue recycling for different prices of carbon, essentially different carbon price pathways going forward. And what was interesting was that although they resulted in relatively similar magnitudes of carbon reduction and impacts on the economy, they had very different impacts within the energy sector itself. Some of the models had essentially proportional impacts across all energy types, across all fossil fuel types. Coal went down, gas went down, oil went down as the carbon price increased. Other models that could substitute the end-use fuels saw actually coal declining faster and being replaced by gas. Now, in fact, this is what we're seeing. This is what we've seen since 2005, this coal-gas switching. The big question was being able to represent that physical phenomena. I think you were talking about the physical constraints in the energy sector, Carey. Being able to represent those physical realities in the energy sector, the fact that you can switch coal for gas, but it's much harder to switch either coal or gas for oil in the transportation sector, let's say. Is that important in looking at the energy macro couplings?
Oh, right. Yeah, I guess it's easier for me to say, yes, it's important, harder to say how you do it, right?
How important is it? Of course it's important. How much does it drive the both? I mean, those are the fundamental questions we're trying to get after.
Oh, right. So I think that's a great question. And in my own modeling, so on the, at least maybe a last comment here on the aggregate production function, at least some of the work I've done and what kind of brought me into the energy and macroeconomic modeling sphere in general was looking at the concept of net energy, or what we would call energy return on investment, right? How much energy does it take to make energy? How much diesel fuel and electricity do you have to consume to drill an oil well? Or how much electricity do you consume to make a solar panel? And how does this relate to in some sense, the purpose of the energy system, which is to extract resources from the environment and then hand these over to, in some sense, the rest of the economy to function in their machines. And so energy return on investment is one way to think about that. And to me, if you're going to do this, you have to have, in some sense, two sectors, or at least you have to define this within your model. And one way to do it is to define two sectors instead of one aggregate sector. You at least have two. One's job is to extract stuff, and one's job is to consume what has been extracted and what is left over. That's at least one step more complicated, but that's a question in my mind of whether something like that is necessary, and incorporating the idea that, well, let's just say the deeper you drill for something, in some sense, the more work you have to do. And if you factor in that physical necessity, you can get that feedback on increasing prices if you would like. So any comments on that, or whether we should be incorporating sort of these physical feedbacks within economic models to either inform prices or be compared to prices?
Well, of course, that's where all the electricity models are going right now. What you're describing is essentially the duck curve in California, where you've got negative prices and very low prices, and sometimes negative prices in the middle of a day. And can you do time arbitrage? Can you buy energy very, very cheaply and then use it another time or in another place or another mode, another application where it's more valuable? And you can, if you look at it through the lens of energy invested for energy return, you can end up with these apparently perverse situations where you're consuming maybe even more energy than you're producing. but that the explanation for that, or the explanatory power, comes in when you look at the prices of those things. If you can get a type of energy, and a type of energy might be electricity bought in the middle of the day. If you can buy it very, very cheaply and use it somewhere else very, where it's more valuable, I think an economist would call that an efficient allocation of resources, wouldn't they?
Steve, anything?
Well, I've got a fundamental perspective on whether we should include energy in economic models or not, and that is that we need physical reality in economic models, and we don't have it right now. In some ways, the CGE models, which were displaced by dynamic stochastic general equilibrium models, at least had the fact that one sector depends on the outputs of other sectors, so there was a level of physicality in economic models. DSG has taken us completely out of that realm, and you have the Ramsey growth model as a single commodity abstraction, which has led to the models that people like Nordhaus have developed, which just use the Ramsey growth model and presume equilibrium through time. And I can't help thinking of the South Park cartoon involving the garden gnomes deciding they're going to steal underpants and profit. They had a 3-part plan: 1, steal underpants; 2, question mark; 3, profit. That pretty much describes the neoclassical models, because if you look at them, they have temperature change, question mark, GDP fall. And the question mark, they're filling their own nonsense into the question mark. And we have this debate now about how many degrees temperature will cause how many degrees a percentage fall in GDP, which is completely rarefied and removed from the real world. And of course, as you'd see, from my paper, I'll give it title, like the appallingly bad neoclassical economics of climate change, fabricated data that is massively understated. If we at least had some physical links in the production system, as we used to have in CGE, you couldn't make up the level of, and part I'm going to go Australian here, the level of bullshit that exists in the modern neoclassical models of climate change. So I want the physicality there.
So David, I guess in terms of the net energy, I was thinking a little bit differently than maybe net load or negative net load, as you were implying. Let's just say something like oil sands, right? If it's you put in 1 unit of heat and some other energy to heat the oil sands and extract it, and you get out maybe 5 units of heat energy in the barrel of oil, which is different than, say, a ratio of 20 for historical oil and gas, that inherently sort of translates to a higher price, and that we could perhaps incorporate these ideas. I'll go to one more topic, then we'll go to more of the questions. So thank you for the questions on the webinar. So one thing that fascinates me, I think it fascinates both of you as well, is there was essentially, David, you mentioned models and to a large degree are calibrated to some historical data, and in some sense they're a reflection of pushing those trends into the future, and we can use that information, caveat emptor, understanding what they're doing and what they're not doing. But there was a significant change in let's just say the trends in the 1970s, right? And almost every economic and energy trend you look at is sort of growing tremendously, say from the year 1900 to the early 1970s. And then it has this sharp change. It's, 1973, energy consumption per person is increasing in the US 4% a year or so, and then it's constant after that. And this has implications, or there are reflections in the economic data. Let's just say the wage share. We have this discussion about inequality in the United States. The share of GDP going to wages was flat until constant until 1970. And then after that, it's been declining at a slow linear rate. When I plot energy consumption per GDP in the US, or energy consumption per person, in the US, and the total compensation to employees, including their benefits, they almost follow each other exactly. So I'll start with Steve and then go to David. How do we think about these economic trends, which seem to change, or many important economic trends seem to have changed in the 1970s with energy trends? And do we really have a grasp on whether energy is this explanatory linkage that maybe some economists are missing?
I think we have a handle on it, which implies, and when we look at, say, the case of America, which is saying there, that, there are income distribution and wealth issues about the 70s as well, not just the energy. But that break in the 1970s is seen as quite significant, and you've had like a flatlining for working class compensation since then as well, but a rising GDP while energy per head is relatively constant. So people do expect this, flatten out relationship between energy and GDP over time. But you look at the global level, and the energy, particularly in the context of climate change, energy is a global issue. That all seems to be flattened out over the global level. So you don't find a break from 1970 on. It's slight. It is there at the global level, but far less extreme when you look at an advanced nation like America. And given where we are now, that's the time at which this is happening, with the enormous growth in wealth of India and China and their populations as well, but of course being far below the levels for an average American, you can't imagine that transition being reached by those countries. They're still in the very early stage, and they're so much larger than the West is. We can't achieve that transition for them to achieve an American level of income or an American level of energy consumption. So I think that sets the overall constraint, and we have to. I think we can read too much into what happened in the 1970s in America. If we apply it to what's happening now at the global level, we'll mislead ourselves, because so much of the world is well below the income standards of the 70s in America, aspiring to it. And the question is, can we sustain that level of energy consumption on the planet? The answer is, I think, is categorically no. So I think that we can't expect a transition to a less energy intensive GDP to save us from the pressure we're putting on the planet right now.
Any comments, David?
I think the lesson of the 1970s or even the 1960s, the population bomb, the oil crisis in the 70s, you look at the price of oil in the 80s, geopolitics in the 90s, you look at the price of oil in the 2000s again, the development of the shale revolution, all of these things should give us modelers an awful lot of humility when we're trying to project far forward into the future. We've never gotten it right in the past. We're not likely to ever get it right in the future. That's me saying that as a modeler. I look at the historical record of our accuracy as modelers predicting the future. We don't do very well at it. But that's not really the point. I know it is the point, but it's not what models are useful for. If you look at what models do, they're calculators that when you put in the relationships that we've observed historically and you project them forward, what they will tell you is this is how the world would evolve. It's not how the world will evolve, because all kinds of things will blindside us. We know that. If you look at the disclaimer that nobody ever reads, the one that EIA puts out is that the AEO, the IEO, these are not forecasts or not predictions of the future. They're projections of what would happen if everything stayed the same. And specifically what they mean by everything stays the same is current laws and regulations stay on the books as they're written and don't ever change. That has never happened historically. We know that they're going to change in unpredictable ways, maybe some predictable ways. I think that's thing number one. And thing number two, technology. There are no technology breakthroughs. Again, we've never had a period in history where there have been no technology breakthroughs. Technology breakthroughs come all the time. So the one thing we know is that the two basic assumptions that EIA puts into their projections, and that frankly most other modelers put into their projections, either with or without saying so, are ridiculous. They won't hold. So what good are they? They're not going to predict the future. The value that they provide is that they give you a baseline against which to measure change. So if you get a wrong projection going forward, okay, you know it's going to be wrong, but how different would it be if you changed something? How different would it be if you made an additional investment in some technology A? How different would it be if you imposed a policy on top of this? It's not that the baseline projection is right in any sense, that's where we're going. It's that the difference between that wrong answer and a different wrong answer with some kind of a change to it, that difference is much more likely to be correct. From an error analysis standpoint, essentially what we're saying is that the projection has all kinds of errors associated with it that are mostly unknown. But a small incremental change about that baseline projection has largely the same errors. So when you do the delta between them, when you take the difference between them, most of those answers are errors are highly correlated and they cancel. And what you're left with is a delta, which has far more accuracy than the projection itself. So what the models can do essentially is they can show you changes that would happen if you made a change in the initial conditions. What should you do? And frankly, that's how models should be used going forward, to figure out how to design policies. What direction should we be steering the boat? Not what's the compass heading that we need to go in. We're going to get that one wrong. But should we be steering a little bit more to port or a little bit more to starboard? I think models can really help us answer that question.
Right, and I think our difficulty is knowing who's got what assumptions behind their model and others. There's just so many, and from an outside observer, policymaker or NGO or something, or even me as an academic, it takes a lot of effort to know what's behind any given model. I mean, the paper I published earlier this year, essentially, like you're saying, if these assumptions hold and I have this internal constraint on energy and this energy return on investment feedback, and you eventually get to from a growing to a constant per capita energy consumption, given my assumptions and that's going to happen, here the wage share was demonstrated to be flat and then decline, just like experienced in the US. No way I could have predicted that was going to happen in the US. I would have no idea at the time. But given those structures, there's some potential explanatory power there. I'll maybe pass this next question and we'll go to the questions online after this one. Any linkage between energy consumption or the cost of energy or availability of energy and how we should think about debt? Oh, I guess actually Steve has dropped off with his bad connection.
Oh no.
I noticed he turned off his video, but he's dropped off. So we'll see if he comes back on. For those on here, Steve is in Thailand, so we have a and David, you are back in Sweden, right? So,
I am, in fact. Right, we have a global panel today.
We got a global panel on a global topic. So I'll go to some of the questions here from Q&A. One, we talked about this one-to-one relationship in the historic data for several countries between useful work and GDP. And so the question is, will this hold in the future when we're more reliant on digital services and technologies? I think that's just a definite question. And I think one of the other difficulties of answering this question, I can imagine there will be differences. One of the differences.
Sorry about
that. Oh, okay, Steve, you're back. Thank you. We're asking a question here about whether we think from online, whether we think the one-to-one relationship between useful work and GDP will hold in the future, which is more reliant on digital services and technologies. And I was going to say, my initial thought is just the changing definition of GDP itself is a difficulty here. So let's just say incorporating financial services or net interest into GDP now when it wasn't incorporated in the past. This is kind of not a direct, obviously useful work kind of concept. And that makes it more difficult to think about how this is going to hold in the future. But digital services
I think
require energy for energy processing, right? Energy is required for information processing. So there is a physical link, but this is a good question. David, go ahead.
Well, you brought up a point about the financial services, and I just wanted to point out here that a lot of the macro models are incorporated, especially after the financial recession that we had, the crisis that we had back in 2010. Prior to that, a lot of the macro models hadn't included financial services at all, and now they're starting to incorporate them. But it kind of reminds me that we're always fighting the last war in this game. We're always kind of looking at, well, what caused, how did our models break down last time? Okay, well, we'll incorporate that. But we're always sort of one influence behind. And I think the question is, going forward, what's gonna influence? And those are, of course, the big questions. But what can we do other than be fast followers?
Steve, your thoughts on one-to-one relationship of useful work and GDP into the future, and as well as maybe just thinking about debt. I was asking you a question when I realized you weren't on. How do we think about debt trends before, let's just say, 1970 and after the 1980s, and any linkage to energy costs and consumption?
Yeah, well, on the one-for-one, I think what we face is so immediate in terms of the global warming hitting our societies, and I'd see it happening in the next 2 decades. And over that period, you've still got the attempt for the aspirations, if not the continuing attempt for China and India to continue growing, I think we're going to find that their increasing energy needs will maintain that one-for-one link. What we may see is a change in the link between GDP and carbon dioxide, because that transition is happening quite rapidly now in terms of the improving efficiency and dropping cost of photovoltaics in particular. But I think overall that relationship is going to remain there. You have the reason you can see a turnaround in places like America is people, generally speaking, had sufficient material goods. You've still got, particularly India, a large part of the world without those sufficient material goods. And when you've got to use energy to convert raw materials into those physical goods, you've still got that strong one-for-one dependence between useful work and energy. So I can see it being maintained at least for the period that matters. If we get through global warming, which is a big if, then on the other side of it, yes, I can imagine that break occurring when you've had a substantial increase in the income level of the number of people on the planet at the time, whether that's more or quite possibly less than we currently have.
All right. So there's a question of how many people can be, part of the service economy versus everything else. Yeah. And I guess you're
on the debt thing, you mentioned the debt question as well. David, one of the reasons that people are always fighting the last war is they didn't see the previous one coming, and including financial services in macroeconomic models is a sin of the neoclassicals, because they're the ones who didn't have it there. Anybody who were doing work based on post-Keynesian work or particularly Minsky had the role of the financial sector in their front and center right at the very beginning. So when they were saying we're updating after events, we're saying we bloody well told you so beforehand.
Right. So go back to your, I guess, more information and digital services. Steve, I think you're pointing out that, well, if we're going to use more processing power and more servers and computers and things, then you have to make them first, and that requires energy. And is that a reason why you'd expect the one-to-one relationship to hold?
Yeah, there's also, I mean, lots of Indian households want to have their first car and their first air conditioning system, and you've got, and to make those, you've still got that one-for-one energy to output link. You can see it being out one to less than one for digital services if we start making that a large part of GDP. But with the income raising issues we're looking at for the developing world, they still want the physical products.
Right. All right, I'll go to another question here. It's a question about how to model energy investment and production, where maybe this is more post-Keynesian. Investment is some function of expected prices or a function of profits over some long-term time frame. So this question is also about short-term changes and long-term, and how do we think about short-term modeling versus long-term modeling? So how do we model this heterogeneity, the questioner is asking, of investment by different actors, companies? Could be Saudi Arabia versus shale production. Shale production may have more short-term horizon. Saudi Arabia may be thinking a longer-term, decades horizon, but it may be more in general, energy GDP relationships, short-term versus long-term, and including investment. So David, any thoughts on that first? And then
look, obviously the difference in a short-term model and a long-term, medium-term or a long-term model are very different. The influences are very different. Even the structure of the model is sometimes just radically different. At EIA, they use different models for short-term, medium-term, long-term. They think about it very differently. Marrying those things up is usually pretty tricky, just because the principal determinants are just very different in those time periods. On investments, one of the couple of things that are interesting there. We often think about the energy investment the investment in the energy system required to enable some kind of a transition. In fact, a lot of models or optimization models are minimizing, the investment needed. What's the lowest cost system that can achieve a particular end goal, low carbon goal, let's say. When we do that, we seldom couple that with a macroeconomic model where we're saying, look, we're making this investment in the energy system that presumably we wouldn't have otherwise made. We're making it in order to achieve a societal goal, but that means we're taking investment away from, its other purposes. I am unaware, there may be some, but I am unaware of any macroeconomic models that look at that investment that has been redirected into the energy system away from its most efficient use because presumably it would have to be redirected in order to serve a societal good and not a purely financial one, and what impact that has on the rest of the financial services sector if you take that the capital is constrained in some sense. But Steve, maybe you know more about that.
Go ahead, Steve, unmute yourself.
I lost a bit of that through internet problems, so can you just give me the gist again quickly, David? Sorry.
I was just talking about the efficiency of investment. We talk about investment needed in the energy system to enact a transition. We very less often talk about how the redirecting of that investment into the energy sector or into specific investments in the energy sector impacts the rest of the financial sector, let's say.
I think we tend to have a belief that there's a fixed pot out of which investment can occur. And if something gets more of it, then some other part has to get less. That has us thinking that we're always at a level of full capacity utilization, and that the financial sector has a limited bundle of funds that can be used for production. I think they're both wrong. We normally operate well within the physical capability of the economy. This comes out of neoclassical, again, thinking of how the economy operates, which has this idea of rising marginal costs because of diminishing marginal productivity. When you research firms and you ask what they've got, they talk of declining marginal cost. So they operate well within capacity. So they have about you look at take a look at the capacity utilization figures for the American economy, you'll see that that's been trending down radically over time, but it's never been higher than about 90%. So there's an enormous amount of spare capacity around, which could be mobilized by the financial sector. And the financial sector itself creates money, as does the government, which can mobilize it. So I don't think we face either or. I think we just simply haven't, certainly in the area of the transition to renewables, and for that matter, nuclear, we haven't allocated, but we haven't thought it's important. And it's really what Marx called the dead hand of the past. With our inefficiencies come out of the political dominance of the fossil fuel industry and their ability to keep us in fossil fuels and to minimize the dangers of those when we could have been making a transition much more rapidly. I saw one of the questions about the limits to growth study inside there. Both the oil industry and the coal industry and the economics has played a major role in disparaging those warnings, saying don't do anything about it. So I think the inefficiencies have come out of that rather than the absence of funds.
Oh, right. So yeah, I'm going to read this question here. I've been told we can go a little after the hour time frame, so I'll ask one or two more questions and go over here. You point out the comment here. I'll just read this question on the limits to growth, or the World 3 model. Any thoughts on that? Is the question that made it so accurate over several decades. There's a few people who have looked at this, Graham Turner and Tim Jackson as well, that basically look at it and say, well, that model was very broad and looking at global trends. And when we compare them, even now 50 years later, to the original work, it's not that far off. Like the general trends are correct, at least at the global level. So the question, was it the amount of physical feedbacks incorporated into the model that enabled this? There's no financial sector. There's not even a government sector. There's no explicit tracking of money in it as we think about it in the modern sense. But what they did have was a concept like energy return on investment, a concept like if you deplete their non-renewable energy resource or their fossil resource, at some point you have to allocate a higher fraction of total capital, or which was just to say a higher fraction of total investment in some sense, to the purpose of just extracting resources. And that flow of resources is fundamentally the constraint towards however much money you generate from a government or from a bank issuing a loan. They can issue as much money they want, but that value of that money, if you will, is going to be dictated by the actual flow of resources. I think that's the way I interpret their inherent structure, but they didn't model debt explicitly and these kinds of things. So that's also related to my previous question on two sectors, or at least this energy return on energy investment feedback. And I can say the World 3 model has influenced me in my other reading to say, that seems really important to me. When I run a model, I want to have something like that structure in there. So Steve and then David, for any thoughts?
Yeah, I mean, one thing which one of the many pieces of fake news that William Nordhaus has got away with is the claim that the limits of growth wasn't based on data. These first papers called measurement without data, and that's garbage. What actually happened was a decision, an editing decision by the editors of the book to not to include the data fitting exercise, which fitted it to obviously a set of indices from 1900 to 1970, and then they ran the model forward from that point on. So the actual fitting of data wasn't included in the book itself, but the fitting of data was essential to the validation process for the model. It wasn't released until it could reproduce the results from 1900 to 1970 reliably. Then they ran it forward from 1970 to 2100. So I think it shows the importance of getting your system relations right, because that's fundamentally what limits of growth is about. It's the feedback of one system state on another in a dynamic non-equilibrium setting. And by backcasting the data at one extreme to get the parameters, and then having the interactions between the system states for the model, they did an extremely good job. And the only reason I think we've done so badly in economic modeling since is economists disparaged that approach and let it die on the vine while they continued fertilizing their own approach, which has led us into the impasse we're in now.
So just for documentation, I think the book Dynamics of Growth in a Finite World is the technical version that has the graphs and calibrations of the World 3 model. David, anything on this topic?
Yeah, look, I'm not going to talk about whether that model has any validity or not. I think from my perspective, I look at how useful it is. I'm not sure I know what to do with it. It doesn't really tell you what policies to do. How would you transition to a low carbon economy? From my perspective, I don't know whether it's right or wrong. I don't know how to use it. However, that doesn't mean I don't like it. What I like, what I'm personally in favor of, is a heterogeneity of models. I have tremendous respect for the GTAP database, I got to tell you. But when you look at half a dozen models that are all based on the same database and they tell you the same answer, that doesn't really tell you very much. They're all based on the same input, so of course they believe the same relationships. Of course they're going to tell you the same answer. What I like is a heterogeneity of approaches, a heterogeneity of structures, a heterogeneity of input data, input assumptions, implicit and explicit assumptions, representations of the energy system, and then look at this ensemble of heterogeneous models to have the ensemble tell you, when you make a change, how does that change percolate through the energy system? How does that change percolate through the economic system, feed back on the energy system? When that ensemble of heterogeneous models tell you the same answer, then you can be assured, you can have a lot more confidence that that answer is robust. When they start diverging from themselves within the ensemble, that's when you have to start being careful. And in my experience, when I have seen people actually test this, and they test it in places like the Energy Modeling Forum, they find that unfortunately the models start diverging from each other far sooner than we get to a low carbon world. What I learned from that is be very, very careful when picking a model to model a transition, because any individual model may or may not be able to model that well. Instead, it's far more useful to me to understand when the models are reliable and at what point do they start breaking down and become unreliable. What I think is really interesting from a societal standpoint is that we know where we're trying to get to. We know the goal that we're trying to get to, this low carbon future. It's much less certain what the pathway is to get to that goal. And when you have people that can tell you, I can tell you how to get there, that's when I tend not to believe them.
I think it's worth pointing out the meteorologists certainly use that approach of an ensemble of models for their much more reliable predictions about weather dynamics than we manage in economics.
Yeah, and that's a physical system. Economic system that depends on people's behaviors, so all bets are off.
So importantly, so I guess you say, how do I use something like the World 3 model the way I think of it, or at least use it in my own head? I'm not making investment decisions, right? But for my own work is, if this seems to have some general tendency about the global dynamics that other models don't have, say based on neoclassical or exogenous assumptions of technology growth, this one doesn't have that, and it better represents the trends than I think that's most important feedback is this sort of net energy or energy return on investment dynamic. It's a physical thing that therefore influences prices and therefore influences behavior David, as you say. So at least that's my takeaway on it. We'll go to one more question and then we'll wrap it up here. So thanks for the questions. There's more than we have time to get to. Oh, this is a good one. Pretty fundamental question, I guess. Renewable energy across the board has a high capital cost as opposed to traditional energy sources, which have high marginal short-term costs, such as fuel costs. So this necessitates long-term thinking and more credit, and this inherently brings risks, but also necessitates planning, or potentially, and necessitates planning from the state and not from the private sector. So how can we think about the transition? So we got capital-heavy investments, and is this the role of the private sector, or how much is the role of the private sector versus state-level governments? We'll start with David and end with Steve.
Yeah, it takes a lot of planning, and planning usually involves long-term models. These are on the order of 20, 30, 40, 50 years when you're building out, wind and solar. What worries me about those planning models is that they assume things like constant declines in costs. And that, it reminds me, the rhetoric just around renewables right now. I don't know what's right, but I'm telling you that from my perspective, the rhetoric reminds me very much of the rhetoric around nuclear in the 1970s. Remember when nuclear was going to be too cheap to meter? We weren't going to have to worry about energy supply. It turned out that wasn't true. The costs turned around and started increasing for nuclear, and now it's too expensive to build. Right now, the energy cost of wind and solar is declining, and it's going to zero. If you look at the trends, I can do a learning curve as well as anybody else, and the EIA does put learning curves in, and they have the cost of wind and solar decreasing over time. But what I haven't seen a lot of people doing, there's a few people that are starting to do it. EPA is doing it, EIA is doing it, NREL is doing it, EPRI is doing it. They're getting together and talking amongst themselves and doing it. But they're talking about how do the costs increase over time as penetration increases. And it's not just physical costs, it's not just interconnection costs, it's not just grid stability costs. It's things like just like it was with nuclear. What do you do with protest groups? What happens when you put up enough wind turbines in flight pathways that you start declining populations of migratory birds? We're seeing that. It hasn't hit the popular press yet. You haven't had another Rachel Carson write another Silent Spring about wind turbines. But what if you do? What happens then? Are there limits? Not fundamental limits to this kind of growth, but are there societal limits? Is there a limit to how much society will accommodate, will accept these kinds of new energy resources? I don't know. No one knows. But what I'm telling you is that in the models, no one's putting that in. They're effectively putting in zeros, and that part I know is not right. It's not zero.
Steve, before you go, let me make one comment there. So, in some sense of, let's just say, a public pushback to infrastructure in the environment, I actually do consider that a physical thing, in the sense that the Earth doesn't have an infinite surface size, and if it did, then we could always be infinitely away from a wind turbine or a transmission line, and we're not. So I still consider that a finite world effect. And here at the Energy Institute, University of Texas, we do have an online tool, the Energy Futures Dashboard, that helps explore some of these things, at least counts a general land use metric and lets a user choose their future energy supply, which could be like 100% renewable. And then it gives you feedback on the costs of doing that. It's not a least cost optimization. And thanks to USAE, we had a webinar on this as well. So I won't go on it any longer, but just to inform people. And Steve, so we'll end on your thoughts here, or any feedback last minute from David on capital costs.
I've got a lot of engineers on my Patreon site, and one point a lot of them make is that the usual progress in capitalism has been to use resources and human civilization in general, to use sources with a higher energy density over time. And the transition to solar and wind, of course, is using lower energy density than the fossil fuel period. And that is a dilemma. The amount of land area would need to devote and so on is not an easy issue. And therefore a lot of them argue in favor of nuclear, and I see a lot of talk about thorium reactors. And my feeling is that given how much we need to make a transition away from fossil fuel-based energy, the capacity to scale up, at least in this transitional period, the capacity to scale up in solar and wind is easier to imagine us doing than a capacity to scale up nuclear. We just don't have, if we had enough nuclear engineers and companies to build nuclear power stations, then I'd be a great advocate of nuclear now to make up that base load. But I just can't see it. So even though I know the energy density is a major issue going in the wrong direction, in a sense from high to low, given the fact we've overdone our reliance upon fossil fuel, I think the fastest way to get away from that is still going to be solar. These want to roll out, but of course, it'll have problems in the future, as David is saying, because we're looking at the stage where the design phases are still radically reducing cost, but the deployment phase, as we increase the scale of deployment, may lead to costs that rise in the same way that nuclear did.
And Steve, with the question also included something on essentially the capital cost heavy as a percentage of total investment for
I mean that's important. Yeah,
private versus public funding.
Yeah.
Do you have any thoughts on the difference?
The public definitely, because I mean I've seen some of the estimates of the level of capital cost of power stations of any type. The actual monetary cost of capital can be 1/2 to 2/3 the actual deployment cost. So in that situation, the state's capacity to create money, there is what the mechanism modern monetary theory describes, and not need that return on investment component or risk component to the discount rate, makes the state provision of the money for it much more sensible than relying just upon the private sector.
Okay, we'll end it right there. David Daniels at Chalmers University, former Chief Energy Modeler at EIA, and Steve Keen with University College of London. Dave at USAEE, I'll pass it back to you to wrap it up.
Thank you, Carey, and thank you, David and Steve, really for your expertise today. This is a discussion we could continue for the rest of the day, I tell you.
Or not in my case.
Very grateful for your expertise. For those listening, please be aware, for your friends and colleagues, we have recorded this. It will be available complimentary on our webinar rewind page later this afternoon. A reminder to those listening, we encourage you to visit USAEE at www.usae.org. Consider joining our society. We welcome you to be a part. With that, I officially close this webinar. I wish you guys the rest of your good day or evening. Bye now.